So remember to solve a linear programming problem using the corner point method. The first thing we got to do is find the corner points. That's step one. But to find the corner points, we have to graph it and figure out where the lines and intersections are. So our first one, 4x plus y, we're going to graph 4x plus y equals 8. What's the x-intercept there? 2. What's the y-intercept? 8. Are we making a solid or a dotted line? Solid. Let me bring my ruler. Oh well. So this is 4x plus y equals 8. If this is doing it again, we might have to stop recording. I don't like that. I don't know why it's doing that. How are we going to shade this? Are we going to shade above or below the line? So 4x plus y, is that greater than or equal to 8? Yes. We're going to be graphing above the line. So again, if we put our test point 0, 0, which is below the line, into the inequality 4x plus y greater than or equal to 8, it makes it false. So all points below the line are false, which means all points above the line are true. Notice I only have to shade in the first quadrant. Why? Because you have the non-negative constraints. The x and y are greater than or equal to 0. Very good. So I don't need to go outside of my first quadrant. All right, the second one, x plus y equals 4. What's the x-intercept? What's the y-intercept? Also solid. Am I shading above or below that line? Above. 0, 0 is below the line. It makes it false, so we'll shade above. Same as before, only keeping our answer in the first quadrant. All right, the last one, 2x plus 10 equals 16, has an x-intercept of and a y-intercept of 1.6, because that's 16 divided by 10. Are we shading above or below that line? Above. Again, do not always assume it's going to be above when it's greater than or equal to. You need to do your test point each and every time. So your final answer happens to be the one above all three sections. What I'm going to do is I'm going to erase what we don't need. Please understand, your feasible region cannot cross any boundary lines. Ever. So if you have a feasible region that crosses over, it's incorrect. How many corner points does our feasible region have? We have an x-intercept here, a y-intercept, here, that's a corner point. We have these two guys, and we have one down here. Two of which we know, because we found them by finding x and y intercepts. Two of which we're going to have to find, and remember the shortcut is you can just use your RREF command in your calculator. So we already know 0, 8. And we already know 8, 0. So if you would, find these other two corner points using the RREF command in your calculator. Keep in mind, you have to figure out which lines are intersecting that gave you those points. So that's why labeling your lines is crucial. Also, do not assume that it's a nice and pretty number because your graph may be incorrect. Now, in your list here, you only are listing the corner points. So if you put something in there that's not like 0, 4, you're going to lose points because you may be putting in a value that gives you the highest or the lowest, but you don't want it to give you the highest or lowest because it's not actually an answer. So please make sure you only list the actual corner points. So what does the blue and the orange line give you? So the blue and the orange give you 4/3, comma, 8/3. And how about the blue and the green? The blue, the orange and the green. Very good. It gives you 3, 1. So step 1 in the corner point method, find your corner points. Step 2 and 3 go hand in hand. You're going to make a chart, which I think is the easiest. And you're going to put your corner points into your objective function. If we plug in 0 in for x, 8 in for y for the first one, what do we get? 32. If we put in 8 in for x, 0 in for y to the second one, what do we get? 24. 4/3 in for x, 8/3 in for y. You can give me a decimal if you want.
10.67 plus 4. 4 plus 10.67.
So 14 2/3. And 3 in for x, 1 in for y. Yeah, 13. So that's step 2.
Decimals, right?
Yeah, that's fine. So 14.67 is fine. If I said round to 2 decimal places. All right. Step 3. Are we trying to maximize or minimize our objective function? Minimize. So of those 4 numbers, which one's the smallest? 13. So 3, 1 is called your optimal solution. And 13 is called your optimal value. So you may have to interpret these values, which we'll be doing in the next section.